In this lecture, we are going to talk through orbital shapes. And just to kind of give you the basic foundation, and then we're going to build a lot on top of it. The shapes that we're looking at are going to be the s orbital, which is just a sphere, the p orbitals, which look like figure eights kind of, got some shading like this. We'll talk about the shading. And d orbitals as well. And these are the ones that I can draw well. And then also f orbitals, which I can't draw most of them well, but the one I can kind of do okay is this one. Yeah. So we're going to walk through each of these. But first, we're going to talk about what is this orbital. And I remember in my own like introduction to chemistry, really struggling with what was this orbital thing we were talking about. And and I think the reason it was easy to struggle with this concept is because it feels very vague as a new learner to chemistry. That when we are talking about an orbital, we are talking about the space an electron is likely to be near the nucleus. And so that shape of space that it might be in will change with its different quantum numbers. So as that n level quantum number increases, it changes the shape of the space that electron might be in. And as L changes, that shape changes. And as M sub L changes, the orientation of that shape changes, right? And so that we refer to that space where it's likely to find an electron as as the probability or the probability density of an electron. And so this comes back to this idea from Heisenberg's uncertainty principle that we cannot know a lot of information about an electron's position and an electron's speed because it is so small that the uncertainty related to that position and speed has to be the product of it has to be larger than you would like it to be, essentially, because that it's inversely proportional to mass. So we're working in a space where we have to rely on probabilities rather than exact knowledge about the location of these electrons. So we have to accept that. And so that means we're going to talk about probability density and electron clouds and other things that sound vague. So the orbital is that vague cloud or probability of finding an electron. And we, when we talked about the Schrodinger wave equation, this right here is the symbol for the probability density of that electron. And we look at radial distribution functions to represent, and here's a radial probability function, the probability of finding an electron at a certain distance from the nucleus. And so we're looking at as you get away from the nucleus, and that's what this bottom of this is, it's distance from the nucleus, what is the radial probability that you will find that electron. And now you might also characterize this as the distance from the nucleus. And if you're strictly thinking about the distance from the nucleus and the probability of finding an electron in that distance, as you go away from the nucleus, that probability drops off. But if we're talking about, especially the 1s orbital, as that probability drops off, the space around the nucleus, when we think of it as a sphere, that volume gets larger, right? So it's less likely when it's further away, but it's also part of a larger sphere of probability density. And so the volume of that sphere at that point actually tells us what are the odds of finding the electron in that distance from the nucleus, because it's not just a linear progression of distance. It could be over here or over here or over there. You know, you can think about this in a circle. So we'll talk about how that radial probability then tells us about shape. And the simplest shape of this is always going to be the 1s orbital. So that's where we'll start. Now, that distance from the nucleus has also nodes incorporated into it, because the thing we need to remember is that we're talking about the probability of this electron existing in a space, but that electron is behaving not just as a particle, but as a wave. And so we're actually calculating that probability density as a wave function. And so this will have wave-like behavior, which means it has nodes. And those nodes, like right here at the nucleus is a node, is a space that electron cannot exist. It doesn't have any probability of being there. And so as we go up in energy levels, we'll see that we create more and more of these nodes. And these nodes are spaces the electron can't be, which means it can be on one side of the node or the other side of the node and not in between at all. And this is part of what leads to those like, wait a minute moments when we talk about chemistry, is that means that electron can exist in a place, point A, and then it can exist in point B, and it can exist in those two places, one and then the other, without having traveled in between it, if it's through a node. All right, so let's start with the simple version. 1s orbital. So we're going to look at an s orbital, which is the ones that look like a sphere like this, at n equals 1 energy level. So as close as we can get to the nucleus. Its radial distribution function will show a node at the nucleus. And then its probability of being close to that nucleus will sharply increase, and then it will decrease down. And so as you travel away from that nucleus, it'll decrease. And what you're seeing here, that large increase to that maximum at about 52.9 picometers away from the nucleus, is the probability, the total probability is dependent on that thin spherical shell at that distance r. And so when you're slightly further away, that shell has gotten bigger as you get further away because the sphere itself is bigger. So that area is larger. But then that probability decreases the further you get away, that even when multiplied for the volume of a larger sphere, it becomes very small to the point where it's insignificant, right? So it's very unlikely you will find that electron out at 1,000 picometers away from the nucleus for the 1s orbital. Doesn't mean it can't happen because we're talking about probabilities here, but that chance goes down to be very, very small or insignificant. And so that's what we're thinking about when we look at those radial distribution curves. And so now let's make this slightly more complicated. We have our 1s orbital surface. So because it's just that one kind of peak, we represent that as a sphere of electron density away from the nucleus. And we typically show then the maximum right here as a picture. And so each level of n of our quantum numbers has the ability to have a 1s orbital. So they all have a not a 1s orbital, an s orbital. But that s orbital will always have that same shape of just being a sphere. But as we increase in energy level, we introduce new nodes. And as we introduce a node, we are introducing what we call a radial node. And so a radial node, so right here, we're looking at a node, and it's characterized here by this kind of white cutout. Is a node where the electron can exist that is in the shape of a sphere. And so the way that I can picture this for me is as a gobstopper. If you've ever had the candy or ever seen the old movie Willy Wonka and the Chocolate Factory, not the new one. A gobstopper is going to have layers of candy, right? And so you would have like a center that's, let's say, like a cherry flavored like soft candy, and then you have like a purple layer that's great, and then a lemon layer, and then you have an orange layer. And like if you hate the lemon flavor, you can imagine that that lemon flavor is the node. You're happy enjoying this candy until you hit the lemon like layer of it, and then you're unhappy, and then you get past it to grape and you're happy again. And that unhappiness moment while you're sucking on the lemon flavor is your node of 0 electron probability. Right. And so then as you go out up to the next energy level, remember, each time we go up a level of n, we get less and less stable. We're introducing more of these radial nodes in the s orbital. And so something that has, that's in the 3s, so n equals 3, will have 2 radial nodes. In fact, you can say the number of nodes for any of our orbitals is always going to be equal to n minus 1, right? N minus 1 is that L value, that quantum number L that is representing the shape, and it's getting that shape from these nodes. So again, Important piece, number of nodes and its total nodes, n minus 1. And this will be radial nodes plus planar nodes. And we haven't talked about planar nodes yet. So s orbitals have only radial nodes. So let's look at p orbitals. Okay. So p orbitals only exist at the n equals 2 or greater energy levels because our L equals 1 corresponds to our p orbital shape, right? L equals 0 is our s orbital. Our L equals 1 is our p orbital. So our p orbital shape will have n minus 1 nodes, which is the same as L nodes. So these all have at least one node. And their M sub L, this is, remember, our orientation. There are 3 possible orientations, -1, 0, and 1. And so that's going to correspond to the X, the Y, and the Z plane. And so that's our M sub L equals -1, our M sub L equals 0, and our M sub L equals +1. And so we can see in our simplest p orbital where n equals 2, so our simplest, we have n equals 2, L equals 1. We'll be able to have M sub L's, there's 3 of them, -1, 0, +1. So it'll have one node, and this one is going to be a planar node rather than a radial node. And that planar node cuts right down the middle. And what you can imagine in this progression, right? If we have a s orbital like this, if I take a node and I just slice it in half, just like with a knife, right? Cutting an orange in half, that's going to lead to this space, sorry, right here, that is my node where the electron can't exist. And that leaves these 2 halves of an orange on either side. And that's how we get to this shape for our p orbital that looks like a figure 8. And then as we go up in energy levels, our p orbitals will always have one planar node. But let's say we go up to n equals 3, and we would have then 2 nodes. Well, then what we'll see for our p orbital is we'll have our one planar node as before, but then we will introduce a radial node as well, like we saw in our s orbitals. And then we'll have this radial node where we can't have any electron density. And then we'll have electron density again on the other side of it, but still in this p shape. All right, d orbitals. So remember, d shapes, d orbitals are coming from L equals 2. And that means that we can have M sub L's equal to -2 all the way up to +2. So that's 5 orientations. The lowest level that energy level that these can exist in is n equals 3. Because we need to have at least n, and then our L is n minus 1. So if our n minus 1 is equal to 2, it has to correspond to an n level of 3 or higher. And so at that simplest version of the n equals 2, we're going to have 2 nodes. And these are going to be our 2 nodes that are planar nodes. At n is greater than 3, then our d orbitals will always have 2 nodes, 2 planar nodes, and then more radial nodes on top of it. And so what do these look like? This is just like we saw with the s orbital, right, with p. So this time, though, if we have 2 planar nodes, we're not cutting this in half, we're cutting it into fourths. And so we have 2 planar nodes that we can cut into our base s orbital. And we can do this a couple ways. We can cut it like that, perpendicular, but we can also cut it. And if we do that, we can have a couple different orientations. We can also do 2 like this. So the ones where we cut them parallel, that'll equal this one right here and give us this shape that looks like a figure 8 with a donut around it. And when we cut them perpendicular, we can do that in different orientations of the XY axis. And that's going to give us these other 4 variations of the d orbitals, or we can cut it along this way, or we could cut it this way instead, off the axis, sorry. And so we get the d, and here are the names for them, the dyz orbital, which is going to occupy the yz plane, and it has our two planar nodes along it. We can be in the dxy, where we're going to be in the xy plane, and so it'll kind of come at you like this. Then we have the dxz, so it's going to go along the x and z axis. And the dx squared minus y squared means it's going to go in between the x and y. And so if you look at it from top down, what you're going to see for this one, if this is our y and this is our x now, is that it comes right in between the axis. Whereas compared to our dxy, if you were looking top down at it, it would go right along your axis like this. And so that's the difference between those two. And then our dz squared is the pretty one that looks like a weird balloon donut. And so for this one, it's really important to label your x and y axis to look at these 5 different orientations, and for the p orbitals too. All right, now looking at the f orbitals, we have now hit the point where we get past people's ability to draw easily in 3 dimensions. So these occur when we have when we're at the n equals 4 energy level or higher. So that means they have 3 planar nodes. If you're greater than the n equals 4 energy level, you have 3 planar nodes plus then radial nodes, which are like that candy shell of no electron density. And so in this case, what's happened is we've taken that s orbital, and now we have sliced it in 3 ways. So we might go something like this, right, to produce our f orbitals. Or we might do something like parallel like this. And we end up with these 7 orientations going from the -3 to +3 for our quantum number m sub l values. And this is what they look like. And so some of them look like 6 different lobes in space in the xy plane or xyz plane. And some of them look like the double donut with like a figure 8 in between. And so these ones I won't expect you to draw on your own or remember the names of the different orbitals, like y cubed minus 3/5 yr squared orbital. It's kind of a mouthful. I would like you to be familiar with the s, p, and d that we use more commonly. These f orbitals really only come into play when we're looking at lanthanide and actinide elements. All right, so I know this is a lot of information about orbital shape, but I'd like to end with phases of the orbitals. So remember, these are waves. These are wave functions. So that means they're going to have area where they are in a positive part of the wave function and a negative value part, just like in our standing wave right here. And so our s orbital really represents half of a wavelength, right? It is just all in one half of our graph, so just in the positive region. And so our 1s orbital doesn't have any nodes in it, right? And so it's all just one sign for our wave. But our p orbital has 1 node in it right here in our wave. And so we have 2 different what we call phases that we represent when we're drawing by shading them in. And it really just means that they're opposite sides of that node. And so when we have a node introduced, we'll shade one side of it to really show that we understand that we have a node in between where there's no electron density, and that it's then a different, what we call phase. And so here, so if that's the P1, the way we would draw the d orbital, and we draw it with alternating ones, is I would alternate coloring in my phases like this to show that I know there's 2 planar nodes right there. And so then when we put all this together, I think it's important to remember that this isn't just a giant jumbled mess. Like, we pull all of these things out and separate them to visualize them and to solve them mathematically. But all of this is just layered on top of each other. These are a bunch of electrons around a central nucleus in basically a sphere. And so all of these orbitals are overlapped on top of each other. And so that probability of finding an electron, just remember that they're all kind of stacked. They're all part of the same space, and the same probability of space. And as your n goes out, you have more volume that electron might be found in than if you're at the n-1 really close in. But all of these are layered on top of each other. And that's going to help us talk about effective nuclear charge a little bit later in this series of lectures.